Hey everyone, this is Stren from ExtremeRigs.net, and today we'll be talking about the water blocks for the Nvidia GTX780 and Titan. And the reference GTX780 is basically exactly the same circuit board, and so the same coolers that fit the Titan will also fit reference GTX780s. And by reference, that means it's the standard circuit board, it's the standard circuit design that Nvidia ship out to the partners, and then they put their stickers on or whatever. And the easiest way to always tell if you have a reference design, along the bottom here, it's going to say Nvidia. Obviously, if you have something like a classified by EVGA or an MSI Lightning card, those are not going to be reference designs. They have much better voltage regulator sections. They've been tuned to deliver a much higher power level, and because of that the circuit board's different. You can't put a normal cooler on there. Now with Titan, of course, Nvidia said we're not going to allow any aftermarket different circuit boards, so all Titans are essentially the same, and any of the water cooling blocks, if they fit one Titan, they'll fit every Titan. So I wouldn't worry so much about Titan. Overall, a lot of the water blocks are very similar. We're at this point in the water cooling community where designs have, not to say stagnated, but results are always very similar. We saw that in the CPU water block Roundup, where you're talking 2, maybe 3 degrees Celsius between water blocks, between a good and an average water block. Obviously there's some older designs which are not that good, and we see a similar thing here with the GPU blocks, at least when you're paying attention to the GPU core, and that's the equivalent of the CPU is the main chip in the middle, which will sit kind of directly under here, and you'll see it kind of marked out on the back of the board there. That's the main GPU core itself. That's where all the processing is done. And so, what we see in the results is that at higher flows, around 2 gallons per minute, almost every water block is the same. I mean, within 1 degree C. And so to a certain extent, we're no longer choosing necessarily based on core temperatures. Core temperatures are great. Everyone wants to be number one, even if it's by 0.1 degrees, and even if the margin of error is larger than the difference, people still want to be number one, and that's understandable. What I want all of you to think about, though, is what other factors are there? And so, for one of the award winners, I did not necessarily choose the one that had the best performance on the core, because I believe there are other things that need to be considered. Before we dive into the actual thermal results, I want to talk a bit about the testing. All of this is on the website, so if you'd rather read this rather than listen to me go through it, then do that. The website is ExtremeRigs.net. And on the front page there'll be a link somewhere to the Nvidia Titan 780 water block Roundup. So, as I kind of alluded to before, Nvidia changed a lot of things with the Titan. They've been really on this kind of anti-overclocking spree. And it's not so much overclocking directly, it's overclocking indirectly. Nvidia felt that their RMAs were too high, and they thought that it was to do with people overclocking cards, pushing them harder than they were designed to be pushed, and then returning them when they broke. And it's fairly common knowledge, overclocking can reduce your lifetime, and it depends how cautious you are. And of course there'll always be some person out there who decides to run a ridiculous setting that's obviously going to toast their card and then try and get it RMA'd. You know, you're never going to avoid that. At best, you'll deny it, you know, the warranty. But that's really it. So Titan was the first card where they put a very strict power limit on it. Now other products have had kind of power limits, but with the Titan, a lot of the cards were hitting that power limit very quickly. You could run the card at higher clocks with not much voltage increases, and in certain cases, the power limit was being hit, and that frustrated a lot of people, particularly when they found out things like turning the fan down meant they had more headroom before they hit the power limit and the card started to throttle back. So, you know, traditionally you bought a water block so that you could either overclock further because you could get the heat out. You know, going back to the GTX780 days where the cards were running so hot on air. And I remember my GTX780s, they were running about 110 C on air, and that's just incredibly hot. The thing was just kicking out hot air like crazy. And so, you know, water blocks were there to say, okay, I can run the card cooler and I can run it at a high clock. Now we're at this point where it's not so much because of the heat, because the Titan cooler itself is very good, and even with modestly, you know, a modestly, I'm trying to say not too loud fan is what I mean, moderate speed on the fan without putting it to 100% on the fan level, the card doesn't get that hot with normal clocks. However, you know, if 6% of your power budget is being eaten up by the fan, it's nice not to have the fan and be able to push the card that little bit harder. And changing your cooler for certain brands doesn't invalidate your warranty. Unlike the BIOSes that are out there that will remove that power limiting throttle. So the reasons to apply a water block now for something like Titan, less so for the 780, have changed a bit from, you know, the traditional reasons. Of course they're still there, and of course these days just the aesthetic is, you know, people water cool because they water cool. It's kind of like memory. You don't need to water cool memory. You don't need to water cool your hard drive, but people do. And at least with the graphics card, it makes a lot more sense than the other two. So enough about that. We're going to move on to the results itself of the different water blocks that we have, and then after that, I'll go and we can zoom on the individual blocks and talk a little bit about how each one performed. During testing, each block got tested once with Watercool and MX2, which is a very good TIM for testing. It's not necessarily the best TIM for the end user who wants the best temperatures. It's a fairly average TIM, but it has some things that make it very good for testing, such as a low cure time. It's very resistant to poor mounting. So that's really helpful when you only have one run of data per card. And you know, originally I wanted to do 3 runs per card, and I was trying to do that, but as is often the case, a card after a large number of mounts can have joints weakened, and so the card was not too happy running at the same operating point anymore. So I had to abandon testing earlier than I'd like. So what I would do on each card was to run 9 different flow rates. So I would mount the block, I would run it overnight to let the curing process happen on the TIM, so that the TIM was fully stable by the morning. So I'd run it overnight, and then the next day I would run 9 data points. Each data point I let run for an hour and 10 minutes. That consists of 40 minutes of warm-up, temperature stabilization, 20 minutes of data logging, and then I would capture the next 10 minutes as well, just in case. but I'd only really use the 20 minutes after the 40 minutes of warming up. And then I'd change the flow rate, and then I'd go again. And I'd always start with the highest flow rate and then go down. So the approximate range of flow that we're talking about is from about 2 gallons per minute to down to about 0.3 depending on the card. I kept the pump setting consistent, so a more restrictive block is going to have a lower flow than a low restriction block. And that's kind of what you would see in your end system. For example, most people don't measure their flow rate in the system and then adjust their pump so that it's a constant number, regardless of the part they're changing. People tend to, well, a lot of people don't even bother measuring their flow. That's a different story. But a lot of people just put it in, they'll estimate what the flow is, or they'll measure it, and then they'll put the components in, or change a component. And you know, people aren't necessarily fine-tuning the pump based on that flow rate. So, you know, pumps are normally tuned more towards noise. So if we take a look at the first block versus the pump setting, and as I said, you know, these 9 values span from 0.3 to 2 gallons per minute, and you can see there's a wider spread at the low end where the flow is more like 0.3, and that's about 4.5 degrees of separation. And then by the time you get down to 2 gallons per minute, you're talking about less than a degree, maybe half a degree C between all the different blocks. Now this is a very useful plot in terms of just saying at a fixed pump power, how does a block react? But for you guys, you don't know as easily what these pump settings at the bottom mean. So if we move this data and plot it versus the measured flow rate, it'll look a lot more like we used to see, whereby instead of it looking a bit more linear, what you're seeing is more of a, I don't want to say exponential, but maybe a logarithmic kind of decay there. You know, the faster and faster the flow gets, the less and less return you have. And you see a similar thing in water blocks. You know, above 1 gallon per minute, you really start to get much less of a benefit. And so for that reason, I don't think there's any reason to change our normal operating point of 1 gallon per minute to 1.5 gallon per minute as the kind of your ideal golden zone of operation. So still trying to aim for those kind of flow rates. Now the reason I tested as low as I did is because a lot of people run GPUs in parallel. If you have multiple graphics cards, you have the option, assuming they're on one loop, to connect them in series or in parallel. So if you have 2 blocks, you could feed the water into one block and let the warmer water come out of that first block and into the second block, and then out of the second block and back into the loop. However, if you run the cards in parallel, each card gets cold water, and then they both dump at the same time their warm water together back into the loop. And they each have their advantages and disadvantages. If you have a lot of cards in series, you're building up restriction. Each block adds more restriction to your loop, so your flow rate decreases. A lower flow rate hurts your performance. However, in a parallel loop, although each card is getting fresh water, unlike the series setup where the next card always gets a little warmer water than the previous card, the compromise is now you're running a much lower flow rate in each card, because let's say you have 3 cards and 1 gallon per minute flow rate through the main loop. Well, now you've got 3 cards in parallel. Each card is going to get 1/3 of a gallon per minute. And so, you know, that effect might be large. However, compared to 3 cards in series, your flow rate through the main loop will be a little higher because you're less restrictive. So often the differences between series and parallel are not that big. And so the choice, you know, these days a lot of people just choose to go with the low restriction option, i.e. parallel, because it just makes life easier on the pumps. If the temperature differences are not that large, why not go parallel? Your pump has to work less hard, and honestly it looks a little cooler too. The only time I would say to do series is really a mixture of series and parallel. If you have 4 graphics cards, I would tend to do 2 in parallel in series with another 2 in parallel, rather than all 4 in parallel. But it's not a big deal. Even if you did 4 in parallel, you'll be fine. So, as we're seeing, you know, at that low flow rate, the EK block, for example, which is pretty much the worst performer on the core temperatures, you know, that's almost 8 degrees centigrade above coolant at your high flow. So at 2 gallons per minute, you're saying, okay, I'm getting about 8C, and then going down to about 0.4, you're getting 14.5. So that's 6.5 degrees of change over that range. So flow does make a difference, but it also does depend on the block. The XSPC is moving much more like nearly 4 degrees. So different blocks respond differently to flow. So if we take a slice through our data and say, okay, we don't particularly care at 2 gallons per minute. Most people don't care, you know, most people don't run there. So let's pick 2 particular data points to look at. Let's look at a very average pump setting. For people with 1 graphics card, they'll probably be running about 1 gallon per minute. And so let's see how the blocks perform at that point in time. And if we do that, we'll see we're running about 8.5C on the XSPC block. So that is 8.5 degrees above your coolant, and that delta is based on a very high power load. I'm running about 123% power on the Titan. And you're not going to get that much power unless you've decided to modify your BIOS. So you shouldn't be seeing any more than those kind of numbers. That is, you know, on this block, assuming you're not really driving the car hard. And then on the low end, we have the EK, which is running about 10 degrees. So we're seeing about 1.5 degrees difference between the blocks, which is really not that much. To put that into perspective, we'd expect an error of about 0.5 degree. So, you know, we've assigned numbers to these blocks, but, you know, imagine there's some plus or minus on these numbers. And so while I do believe the XSPC is bigger than the EK, you know, how confident am I that the EVGA is slightly better than the Koolance, for example? You know, there's some margin of error there, and do bear that in mind. So again, this comes back to the whole the main cooling properties of the block. We got to this point in time where they're all very similar, even though different blocks use different cooling structures. The end result is very similar. So let's move on to 0.35 gallon per minute. Here we see, you know, this is our lowest flow testing point, and for some blocks this meant more like 0.28 gallon per minute, some was more like 0.41. So we're just going to say, on average, it's about 0.35. So this is the kind of flow you might expect in a 3 or 4 graphics card in parallel setup. And in this case, now everything's stretched out a bit more. Everything's running hotter, and the numbers have spread apart. So now we can see XSPC still at the top. Watercool and Aquacomputer, the German manufacturers who generally are used to running with lower flow rates. Americans generally tend to favor higher flow rates. Europeans generally tend to favor quieter systems with lower flow rates, with a trade-off in performance. In the middle we have the American manufacturers EVGA and Koolance, and then at the end we have EK. And this was a bit of a surprise to me. I didn't think EK would be at the bottom here. We used to seeing them kind of maybe in the middle, but I guess someone has to come last, and it's not like it's a bad performance. So, as I mentioned before, core temperatures aren't everything. So I also, tried to measure the VRM temperatures, the voltage regulated temperatures, that is, and the VRAM temperatures. And I did this by using a infrared probe. They call them laser probes, but I don't think it's really a laser. Maybe it has a laser pointer. It might just be an LED with a lens though, so who cares? Point is, I would look for the highest temperature on the back VRAMs, and I would look for the highest temperatures on the back of the board under the voltage regulated chips. And I would measure those, at the end of the test. And what I found was that there were far greater differences there than I expected. For a start, I was measuring the back of the board, and I really did think that therefore ambience would be more of a factor than necessarily the water block, because these chips aren't even exposed directly to the heatsink. The heat sinking effect is through the board and through the RAM on the other side, which is a fairly high resistive path. But if we look at the data, let's start off with the VRAM, you'll see the EK block is now in the lead. Where it was doing the worst on the core temperatures, now suddenly it's doing, 22 to 23 degrees C, depending on the exact version of the EK block. Whilst the worst blocks, Aquacomputer and EVGA, they're about 10 degrees higher, which is a much bigger gap than the 2 to 4 degrees we were kind of seeing on the core. And that gets even worse with the voltage regulators, which you might expect. VRAM doesn't really use that much power. And particularly in these tests, I wasn't overclocking the VRAM, I was running the standard, 3 gigahertz setting on the RAM. So the RAM really wasn't getting that hot. And at some point it would be nice to prove that it was actually the RAM getting hot and not the circuit board. But sadly today is not that day. So if we look at the voltage regulated data, we'll see a similar pattern. You have EK doing very well, and at the bottom, EVGA and Swiftech are really far away. Aquacomputer is also near the bottom. And this difference here is even wider. There is a 30°C difference between the EK and the EVGA Swiftech block. And that's just huge. The EK is effectively providing twice as much cooling. It's probably more than twice, but the temperature delta is half what it is for the EVGA Swiftech. The EVGA Swiftech is up at 62 degrees C, which means if your ambience are 20 degrees, your voltage regulators are running at 82 degrees centigrade on the board, on the PCB. So who knows what the actual chip is running? The chip might be running hotter than that. It probably is. And so I think this is one of the biggest factors you have to think about when you're choosing a block. It's not so much which is the coolest core as how hard am I going to be pushing this card? Am I really stressing the voltage regulators? And if so, I need to factor that into my decision. If you're just running a stock card, you'd probably be fine with most of the blocks there. But now that we've seen new BIOSes that release more power before the throttling occurs, we've seen the hacks to allow the VRMs to be reprogrammed via I2C, and now people are making little programs to do that more automatically now. So that people can run 1.3, 1.4. I think the highest I've personally seen is 1.45 volts on the GPU. And Nvidia didn't design the Titan to run 1.45 volts into the core. And it's not like you can buy a Titan classified where the voltage regulators are designed to do that. And so these VRMs, if you're doing that, are going to be incredibly toasty. If you're running 150% power, 170% power, like I know some of you are, you are going to need to keep those voltage regulated modules cool. And they're, you can clearly see from this graph that some are way better than others. So to move on to the restriction, and that means, how hard is it for the pump to pump water through the block at a given flow rate? How much pressure drop is there across the block? Ideally you want something with very little pressure drop. Imagine a short piece of pipe, and if you were to blow air through it, it would be very easy to blow air through it. But imagine a 10,000 mile long piece of pipe, and now you try and blow air through it, and it's going to be very hard because there's a lot of friction, there's a lot of resistance to that. And the same is true of water blocks. And so in this plot you'll see the pressure drop on the y-axis and the flow rate along the x-axis. And as you'd expect, the higher the flow, the more the pressure drop for each block. And you'll see there's basically three groups here. You have the orange line, which is the Aquacomputer block, and that is by far the most restrictive. And then in the middle we have the Watercool and the XSPC, both with acceptable restriction. It's not the best, but it's not bad enough for us to really kick up a fuss about it. And then at the very low restriction, performing very well in this category, we have the Swiftech in the lead, and then EK closely behind, and then Koolance after that. Those three blocks, all very low restriction, all doing very well on this one metric. So that kind of wraps up our analysis of the performance. And so based on that, they were kind of winners of each category. For the GPU core performance, we've seen the XSPC was really topping the charts there. For the VRM and VRAM temperatures, the EVGA was. For the restriction, the Swiftech was. However, because the EVGA was close enough to the Swiftech, I think the two awards really have to go to both XSPC and EVGA. And I would advise you to get one or the other depending on how hard you're pushing the card. If you're going to be running, close to stock or a mild overclock, I would go with the XSPC. VRMs are designed for a certain amount of heat, and they're not going to die the way a GPU core would. However, if you're going to be pushing the card hard, if you're going to be flashing an aftermarket, well, not aftermarket bias, but a modified bias that's allowing higher power limits, if you're going to be running 1.2 volts and above, I would consider the EVGA. The difference in the VRM temperatures may make a difference. And I would rather have 10 degrees less on my VRM temperatures than I would have 1 degree less on, say, my core temperature. So those are the two I'd recommend. Now we're going to zoom in and look at the actual features of each block a little, and talk about each one in turn. So let's start off with the Aquacomputer block. The Aquacomputer block, well, it's a little dirty here. These blocks tend to get pretty dirty after I'm done testing with them. You can get this in a couple of different varieties. There's the copper version, there's a nickel version, and then you can get a plexi window too, which looks really good. It's a very thin block, which means if the card wasn't a double slaughter, if you could cut that off or something, this could be a single slot block. You can see just how thin it is. One unusual feature about the Aquacomputer, most blocks, you have your GPU core here, and you have your memory here, and then your voltage regulator section back here. Most blocks will give you thermal pads to put on the voltage regulator modules. Aquacomputer doesn't. They want you to use TIM instead, thermal interface material. The same gunk that you put on your GPU core, you're going to be putting on the voltage, the memory. And theoretically, that should provide better cooling for the memory. In practice, we didn't really see it. And that could be because the voltage regulators were cooled so poorly that it didn't matter. One thing you'll notice here, this is your main strip of voltage regulators, and you'll see the stainless steel barely comes there. And so the water really isn't going to be going directly over the voltage regulators at all. Instead, what's happening is that the heat is going to be transferred through the copper, and then it will hit the water. So just bear that in mind. And that could be why the block doesn't do as well on the voltage regulators. It was one of the worst, in fact, on there. Not as bad as the Swiftech. Overall, though, it's a pretty block. In fact, I'd say the nickel plexi version of this is the best looking block on the market right now. It is absolutely beautiful. And if you go to Aquacomputer's website, you'll see that. Otherwise, it's got a removable bridge with 3 Allen key bolts holding it on, which is nice. You can buy different sizes of the bridge to hook up multiple cards. The stop fittings are nice and chunky. The bridge itself is made of palm. The screws, you can see there's standoffs there. You're not directly screwing into the copper, which is a good thing. And these are standard kind of Phillips head screws. So overall, in terms of the design and the fit of the block, I was very happy with it. Did not have any problems. It's very simple to fit. I like that they tried to use the TIM on the VRAM. I'm sad that it didn't work out, but that's life. Overall, it was a solid performer. They do need to work on the VRM temperatures. So let's say EK should be next up, if we're trying to do alphabetical order. This is the original EK full cover Titan block, and they have a second edition, which I'll show you in a minute. This one's had some red dye in it, so there's still some leftover dye, so don't worry too much about the coloring there. This is the plexi nickel version. They have at least 4 different versions. They always have copper and nickel, and then they'll have the plexi and acetal. The acetal normally being black rather than the clear, of course. On top of that, EK have been going through a phase of doing both the plain finish like this and the CSQ finish, which has the circles on it, and it's often frosted rather than straight clear. For now they're doing both, and we'll see how long that lasts, whether they switch one way or the other. So this was the first edition block. The difference with the second edition, and the difference is a small, this one still has a bit of water in it. They're very similar. They share the same terminal block, the bridge, but you can see the plexi extends to the end of the card. The cooling engine itself, the fins, everything else in there is exactly the same. The real change is not just the acrylic going to the edge of the block, but there's a difference in the VRM section. They both have a dual path. So on the second edition, you have a cut through here, the water can come straight out, and then some of the water can go around here. And the same thing is true on the first edition, where it can cut through this little gap, or it can go the long way around and back over. They're a little different, and as we've seen in the results, the difference is really pretty small. You can also buy the back plate. And the back plate is full cover. It's very plain black, kind of satiny. It's not really gloss, it's not really matte. And it lines up, it's the same style, the EK logo in the same place. And this retails for about 30 bucks, which is a little high, but it's not awful. In terms of the back, we do use thermal pads on the memory, and EK is, I think, the only manufacturer that says to also put thermal pads in this section, which is where the inductors or chokes are. And you know, on the stock air cooler, underneath the fan there's actually an air path for those chokes to get some airflow, and when you put a water block on there, they don't get any airflow and they still get pretty warm. And so I think some of what we're measuring when I've been measuring VRM temperature, because I'm measuring the circuit board, for all I know I might be measuring partly the temperature of the chokes, or inductors as I sometimes call them. And I think EK does well for two reasons. Not only because it heat sinks those, but the thermal pads it uses are extremely thin. And of course, the thinner something that conducts heat is, the better it's, you know, the less the thermal resistance. You know, of course there are other factors as well, like the actual conductivity, thermal conductivity of it. But if we were to naively assume all thermal pads had the same conductivity, a thinner thermal pad will always do better. Now, of course, not all thermal pads are the same, so it's not fair to do that. But EKs are thin, and EK is #1 on VRMs. Something to bear in mind. Again, I had no problems with the installation. The block fit just perfectly, no card warp. All the screws are Phillips head. They're black, and the washers are clear, which is nice, but they're not too big, which is also nice. Some of the blocks have very fat washers, and they're very noticeable, and I don't like that. But overall, I really like this block. The next block up is the EVGA hydrocopper. As we saw, this block was extremely bad at VRM temperatures. 30 degrees worse than the EK. So overall I was pretty disappointed with the block, and it's also the most expensive. Now, it does do pretty well on core temperatures. It does at least have that. However, there are also other things I don't like about it. If you have to buy the backplate, this block on its own retails for $170. If you buy the backplate, that's $190. That's a lot of money, considering the Koolance is $129 and has a backplate. The EK, if you add a backplate, I think it's $130. So that's 40 bucks. No, I'm sorry. That's $60 less than the EVGA. So it blows my mind that they're charging quite as much money, and that it isn't #1. If you're charging that much money extra, I mean 50% more than your competition, you best be sure that you're significantly better than them, and this block just isn't. And it doesn't just stop with the price. I don't particularly like this insert. It's shiny versus the matte of the block. I think it looks a bit tacky. The black isn't quite right. It's a bit kind of browny black, whilst this is a very kind of standard cold black. So the insert doesn't match. It has this kind of cheesy big logo on it, and then in the corner it has this kind of milled out section, powered by Swiftech. It's like, well, if you want the Swiftech one, you can buy the Swiftech one and pay, by the way, $20 to $40 less. So I don't like that that's there. I don't like that this clashes matte versus gloss. I don't like the logo. On the edge here, this little EVGA cutout symbol does light up. That I do like. And you know, for a lot of people, these cards are in the side of their computer. They have a window, and in a normal ATX tower you can't really see the side of the card or the back of the card and the back plate. This is often the only part you see, so it's nice that they've made that light up. It's a nice touch. On the back we see the base is chrome plated copper. Chrome plating is fairly unusual. Most people just do nickel. I'm not sure why they chose that. It's fine that they did. This is the connector for the LEDs. It plugs in the 2-pin, not the 4-pin. The Titan, and I assume the 780 is the same way, it has 2 connectors for the air cooler. One for the fan, a 4-pin PWM signal for the fan, and then a 2-pin that lights up the GeForce GTX sign on the side. So I like that they've continued it. The block does come with the thermal pads pre-fitted for you, so you don't even have to cut them out and stick them on yourself. That's admirable, but I don't think it's worth paying $20 for. The thermal pads themselves, they're very strange. They're very kind of stretchy. It's kind of almost like rubber. They're not like most of the other thermal pads, which are much less rubbery. These are very sticky. They're very elastic almost, and I'm not sure if that's part of the problem with thermal properties. They're probably unrelated. But yes, the other thing I didn't like about the block, and you can kind of see it here. There's something like 5 different types of screws that come with this. And the instructions are not quite as clear as they could be. So one of them, there's an additional steel bracket that you can get to, well, not that you can get, it comes with it, and you mount that around the GPU, and that's some added stress relief that may add to the life of the part. I like that one. I'm willing to accept another set of screws just for that, if you have to. Then you have a second set of screws for the main copper block to attach that. And then at the end here, you have another set of screws to attach the plastic to the board. And then at the end here, you have another set of screws to attach to the metal bracket here. So, you know, these do make it stronger. And there's another set of screws too that I've obviously forgotten. But the point is, there's a lot of different screws. All the other blocks only have one type. And why, really? You shouldn't have to have that many screws and make it that confusing. It's just a bit lazy to me. So overall, I'm disappointed with the price. I'm disappointed with the number of screws. I'm disappointed with the thermal performance of the VRMs and the VRAM. But, you know, I think Swiftech really focused on the core cooling, which they did well, but still didn't do the best, and the restriction, which they did do the best, but it's so low flow that I feel like they've compromised everything else in the design to make that happen. And as a consequence, they've given up other things that they didn't have to. So let's move on to the Koolance. The Koolance is it's a pretty good looking block. It doesn't really come across well in photos or videos, but it is quite good looking. It's one of my favorites. I'd still say Aquacomputer is more attractive, but it has the Koolance logo milled out of it. It's not very blingy. Some of the old Koolance blocks, you know, they used to have more plexi in there and they'd have LEDs and stuff. And this is a bit more toned down, which is more how I like them. I don't like to be too blingy myself. So yeah, it's black acetal. You have removable bridge connectors, and now Koolance have finally made different size bridge connectors. And it's nice that they're individual here, because then you can do, oh, I'm going to do a series link here, or you could say I'm going to do parallel coming in here and then split into multiple loops or something funky if you want to. But it gives you a lot of options without them having to charge you a lot, because they have to provide 16 different types of bridges depending on your configuration. So I like that they finally introduced that. The coating on the copper is the standard Koolance type of nickel, and it's a bit darker than some nickels. It's not quite, now some people would call it black chrome, but it's the usual Koolance finish. If you've seen Koolance products before, you'll know what I mean. We've lost some of the thermal pads here, so don't be alarmed that they're not there. Koolance provide two different thicknesses of thermal pads, 0.7mm and 1.0mm. I used the 0.7 as the instructions said, and I certainly wouldn't use the 1mm, because even when I got a tiny kink or anything on the thermal pads, it dipped the performance significantly. So you do want to go at least, well, no more than 0.7mm thick on your thermal pad for the Koolance. Generally, the Koolance is a block that did everything well. It didn't top any chart, but it never really had a problem. It was always sitting comfortably, you know, whether it be core temperatures or VRAM temperatures or VRAM temperatures or flow. It was good at everything. It's a very good all-round block. No problems with it at all. I wouldn't hesitate to recommend it. And the only problem with the block is that the other blocks are doing better. The XSPC beats it across the board on everything except restriction. So if you're thinking about the Koolance, I do think the XSPC is just a little bit better, at least in terms of thermal performance. It does come with a backplate. You cannot order it without the backplate. And that might be frustrating to some of you with GTX780s. For a start, the backplate is not a full cover backplate. If we get the Titan, you can see it's really just designed to line up exactly with the block. Most backplates cover the entire circuit board. It's normally for aesthetic reasons as much as it is for performance and keeping the card straight. And Koolance kind of forgot about that, it seems, because, you know, it doesn't cover the whole circuit board. It doesn't look as good as it could have been. And I would much rather they sold the block individually and then sold separately a bigger backplate for a little more. And the reason I mentioned the GTX780 owners is because this is only compatible with the Titan. If you don't have your VRAMs there with your thermal pads, you might tighten this down too much. And the consequence would be that you might short something out on your board, which is really not a good idea. So, you know, you can only buy this combination for 129 bucks. So it's hard to compete with the EK, where the cheapest version is $100 for the GTX780. And, you know, there is no cheaper version of the Koolance. You're buying, you know, you're spending extra money for this backplate that you can't use. So, like I said, I do like the Koolance block. I do feel like It's a solid performer. No real criticism on it. It's just needs to be just a little bit better to kind of win the award. And it's close, but not quite within reach of that cigar. So we've done Koolance. Let's see. The next one would be Swiftech, but I had to send the block back to Swiftech. But I'll pull out the EVGA to show you the differences. The differences would be, I mean, the thermal performance is exactly the same. The internals are the same. The only difference is the externals. On the Swiftech, instead of this shiny thing, you have a brushed aluminum black metal insert here that goes a bit further. Looks a lot classier. We lose the powered by Swiftech thing there, and instead of saying EVGA here, it has the Swiftech symbol, and instead of lighting up red, it lights up green. Otherwise, it's very similar. The difference is in the packaging. The Swiftech, you get an included backplate for $150. The Hydrocopper, you don't, and it's $170. So the Swiftech is undercutting EVGA by $20 to start with, and you get the backplate, which you'd have to pay another $20 for if you want the EVGA backplate. So really, they're undercutting them by $40. Now, the EVGA includes a couple of compression fittings, but to me, I don't know, I feel like that's a bit worthless, because there are only two. The EVGA rebranded Swiftech ones, and you know, most people like to match their fittings, and a lot of people will have had their CPU loop already, so most people are just not going to use those fittings. And rather they weren't included, and I'd rather the price was lower. So if you want to see the photos of the Swiftech block, you can see them on the website. Unfortunately, like I said, the block had to go back before we got to the video part. So next one up is the Watercool block. It's easy to confuse the Watercool and the Aquacomputer from behind, because you know, the versions I have, they're both copper with a stainless steel plate, and they both have a palm bridge, which is beveled similarly, and the stop fittings are similar too. And the Watercool Heat Killer GPU X block. It comes in a couple of different versions too. You have the nickel version, where the copper is nickel plated, and then the nickel black, which is the same, but this part is then painted black or anodized black or something. That's the whole part. And you can get it with and without the whole plate. And that's just an aesthetic add-on because some people like it. So yeah, again, like the Watercool, it is a very thin block. And if we look at the back, you'll see, unlike the Aquacomputer block, you do have to use thermal pads instead of tin. So like most blocks that use thermal pads, and these thermal pads are very thin. Very strange texture to them too, almost kind of like denim, but not. And then slightly thicker thermal pads on the voltage regulators. Had no problems fitting it. There are some things I don't particularly like. Most blocks, you don't get the screw threads threaded into the copper block itself. Copper is very soft, it's very easy to strip a thread, and I'd much rather strip a screw than the thread of the block, because then you got to throw the block out. Worst case, you buy a new screw. But here, do be careful screwing it in. Now, I think they've alleviated that somewhat by using these plastic standoffs. Now, you don't screw into the plastic standoff, but if you are screwing it in, you can, you know, with plastic, you're going to be able to compress that a little. There's going to be some amount of give, and so that might help a little bit with the, you know, the problem of stripping threads. The other thing I did like, the screws are actually socket caps. So in other words, you don't use a screwdriver, it's not a Phillips head, but you use a hex key, an Allen key. So that's a nice touch. It just looks a little classier, but it's not a big deal. You know, thermally, as we saw, you know, the Watercool, you know, it kind of like the Koolance, really. There's nothing wrong with it. It did well at everything. And it was, you know, second place on VRAM temperatures. It was average at 1 gallon per minute. It was second place at 0.35 gallon per minute. It was average at VRM temperatures. It's a good all-around card. There's nothing wrong with it per se. It's a good product. But again, it's beaten on, you know, on the GPU core thermals by the XSPC. It's beaten by the EK on the VRAM. So it's not going to win an award, but it is still a solid design. Nothing wrong with it. Lastly, we come to the XSPC. XSPC used to be known for very good value products. You know, they weren't necessarily the best performing. Like the Raystorm, for example, when it first came out, it was very good, and then other CPU blocks came and beat it. The graphics card line that XSPC have always been the Razor line. And it used to be that they just used to be copper with stainless steel fronts. And you can see the legacy of that. You have the copper base and then the stainless plate sealing it. However, with the Titan, they kept the Raystorm look on the block. So you have this brushed aluminum plate sitting on top of acrylic. So this becomes a 4-layer stack up, which is going to increase the cost. All the other blocks only have 2 layers. They have the base copper, whether it's plated or not plated, and then they have something to seal the copper. Usually either stainless steel or some kind of plastic like acetal or plexi. But this is 2 layers to do the actual cooling, and then 2 aesthetic layers to give it the Raystorm look. And this acrylic, there's holes for LEDs so it can glow and give you that cool Raystorm look. In addition, the bridge itself, it has a lot of options on it. It has the most options out of any of them. You know, most GPU blocks have 2 ports on either side, one for input and one for output. Well, I say input and output, but you can run the cards either way around. Either way, you have 2 ports for one side and 2 ports for the other side. The XSPC blows that up. It has 7 ports. For this side of the block, it has 1, 2, 3, 4, and this one it has 3. These ones are somewhat more useful, I'd say, than this one. It would be hard to really get tube coming out that way. So I'm not sure really what the point of that is. And I think all these changes do push up the cost. This block is now $120 versus the EK, which is 100 or 110, depending whether you get copper or nickel. It's not just the extra plexi and aluminum plate. It's also these stop fittings. You're getting three more fittings and more machine work on here. And to be honest, I don't think anyone particularly needs it. I also think it looks a bit more ugly. You know, they have these black chrome fittings, and they're a bit chunky. They're a bit, I don't know. I prefer something a bit more subtle, and this is not subtle. It's very functional, but to be honest, to me, it's a bit ugly. The other thing I don't like is actually the backplate. The backplate doesn't match. It's black, it has the logo the same, all that kind of stuff. So in that sense it matches, but it doesn't match the brushed aluminum finish. You know, although it's painted black, you can see these stripes on here. They're subtle, but the backplate isn't. It's powder coated. It's plain black, and it doesn't match, and that bothers me. In terms of the back, it's very standard. You can see the thermal pads there have disintegrated a bit, because I actually ran this particular block quite a few times to make sure that my data was good. there was a lot of suspicion from people that how possibly can the XSPC block be in the lead. Well, it is, sorry. Phillips head screws, pretty standard, and you can see the standoffs are actually brass, so at least you're not tapping into the raw copper. The thermal pads aren't as thin as they could be. I think they would have got better scores on the VRM and the VRAM if they'd done that, but it's not bad. On the VRM it was in second place. Now that's still 10 degrees or so behind the EK, but it's a solid performer, and it's at the top on the cores by quite a bit, relatively at least. So thermally, very good. I do think this bridge is ugly as sin, but a very good performer. So overall, I'd say there aren't any particularly bad blocks here. The one I'm most disappointed with is the Hydro Copper. Less so the Swiftech, just because it's a bit cheaper. Overall, I'd say none of them are particularly bad choices. They were just better choices. And so the ones I'd give the award to are really the XSPC, because of its very good thermal performance all around, and the EK, primarily because the VRM temperatures are so good, and that really matters for those of you who are really overclocking and pushing the Titan hard. So I'm going to leave it here. If you do want more data, it's all on my website, extremerigs.net. And don't forget to subscribe, like the video, all that good stuff. It all helps. And leave me some questions if you have any.